Alright, so we have 2 more gas laws, one today and one tomorrow. Tomorrow we are doing a lab, so make sure you're wearing closed-toed shoes, because we'll be in the lab most today, along with a couple minutes on Dalton's law. So today we're talking about Graham's law, which you guys have on your folder now. Now, I haven't written the equation down for it. It does relate to this little piece that we talked about Friday. After we go through Graham's law, we're going to switch to the last piece of general gas law stuff. It's combining gas laws and stoichiometry. So I didn't think that you guys were capable of doing that Friday. Your brains were okay. So I kind of just scooched that till today. All right. So I'm still checking 1 through 19. So keep that out for me. Appreciate you. Okay. So we've all seen a balloon pop, right? Yeah. We know that the gas comes out. What's the word for the gas coming out of a small hole? Effusion, right? So effusion is gas particles escaping a small hole. Okay, so in a balloon, so you can draw a picture on your foldable if you want to, but in a balloon, if you have a mixture of gases, let's say you have helium and carbon dioxide and oxygen, you've got a lot of gases that are separately trying to escape that small hole all at once, right? Which one will escape first? What do you guys think? Helium, oxygen, or carbon dioxide? Helium. Why helium? No, that's actually not the reason. It's true it's helium, but it's not the reason. Anybody else? It's not the fact that it's not diatomic. It's the lightest, right? So the smallest thing, meaning that's the lightest, is the first one to escape. What is the molar mass of helium? Everybody has a periodic table nearby. It's about 2, right? No, it's about 4. 4. So that's 4 grams per mole. Okay. Who's the next one to escape? Why oxygen? Well, what's the molar mass of both of those? What's the molar mass of oxygen? 36. It's 16 plus 16, so because it's diatomic, so it's 32 grams per mole. And then carbon dioxide is 44. Approximately 44 grams per mole. Okay, so we said the lightest is going to come out first. Why? Well, not just because it's light, but because it's light matters. Any thoughts? Okay, so if I was on the track team, who runs track? Anybody? Okay, so you know the relay race, right, when you pass the baton? Okay, which of the people in your, it's usually 4 people, right? 4 people in your relay team. There's one person that's going to really overall determine your overall place in the track meet. The person who's the fastest or the slowest? The fastest. The slowest is really going to determine, because your slowest is going to slow you down the whole way. It doesn't matter how fast your fast people are, so slow your slow person is, right? I will be that slow person determining what our ranking was. So the weight of these things, lightest, medium, and then heaviest, determines how fast they move. Okay, so one of them is going to hang in there the longest. So who's going to determine how long the balloon stays inflated? Carbon dioxide, right? It's going to stay in there the longest. That first one is fast. That's your gunner, right? That's the person that's out first. They're the one that's going to be the fastest out because they're the ones that are able to travel the fastest. There is a relationship here, and we did talk about this, and you guys were at the end of class, so I'm not sure you actually wrote this down. But the idea is that mass and velocity have a relationship. So M is mass, V is velocity. And since temperature, we wrote down for the ideal gas law 4 descriptors, 5 descriptors, we wrote down that temperature had a direct relation to kinetic energy, right? So if all these particles are all the same temperature, that means they all have the same kinetic energy. Okay, so the only reason this can be the same kinetic energy is if the mass and volume are inversely related. So as mass goes low, meaning it's light, what happens to its speed? It goes up, okay? So light things travel fastest, heavy things travel slowest. All right, so all of that just to say there's a relationship between mass and velocity, okay? And is it a direct or an indirect relationship? Indirect. What's another name for indirect? Inverse, right? So a gas That's what we're talking about here. The effusion of a gas, or the speed of the gas diffuses, is inversely related to the square root of its molar mass. So we're going to take this information and we're going to write it in an equation form. So it's rate, yes, rate, I'm going to put rate 1, but it's rate A over rate B, or rate 2, is equal square root, anybody? Molar mass.
A and B.
Which one is, which is 1?
No, the top is B, and then the bottom is 1.
All right, so this is the inverse relationship. See how it's like opposite of one another? Okay, so this is in your foldable now. Perfect. Other than that, other than this formula, the one thing that you should know is that it's a comparative rate. So we're comparing 2 gases at a time. And the 2 gases actually did 3 at a time here, but we could only really compare 2 at a time. Now, I think on y'all's you maybe put A and B, but 1 and 2 works the same way. Note to self, if you want to make a number that makes sense logically, you always want number 1 to be the lighter gas. And it will always make the numbers make sense. Give me a thumbs up when we can go into a problem here. Most of it, not many of us will be giving us a thumbs up. Alright, majority rules. Okay. So, why does this matter? I like to always make sure you're clear with this. Who's ever seen like the Macy's Day Parade online, or on, like, you know, you see it on TV, because most of us probably don't go. But they have those floats that are really high floating above the skyscrapers. I think it's in New York, right? Okay, so obviously these things are floating. What do you think's in them? Helium. Probably helium. Don't say gas. I knew you were going to say it. Okay. Duh. Okay, there's gas in there, but there's probably helium there making them float. Okay? But if there was helium in there, you know, like this is like meshy. It's kind of like clothing. Gas can diffuse through your clothing, right? Okay, so bad example. So anyway, the float's going to float high because of helium, but it also needs to maintain its shape and form over some time. So what other gases do you think they put in there to kind of maintain that? Maybe oxygen would be flammable. I don't think that they've collected that. Maybe some carbon dioxide. Maybe what's inert? What's an inert gas? Neon. Neon's probably expensive. They probably wouldn't put neon. I heard somebody say though. Nitrogen gas. That's 71% of our atmosphere. So they're probably putting some nitrogen gas and some helium, maybe carbon dioxide, which is going to be the first to escape. Helium, and then, because this weighs what? 28 grams per mole, and then this is 44. Okay, so this is them deflating it, but which gas do you think is predominantly in here? CO2. The CO2, because it's the last one to leave, right? So it's going to kind of hold it down. Very good. All right, so here's your example. Now, I could ask for this in kind of probably 3 ways, but here are 2 of them. I can ask for the rate of diffusion, or I can ask for the relative velocity. Those are 2 ways to mean the same thing. For the comparative rates between hydrogen gas and carbon dioxide gas. So when it says hydrogen gas, what do you think it actually means?
H2.
H2, you guys with me?
Yeah.
Okay, what's carbon dioxide gas, everybody?
CO2.
Okay, let's go ahead and find the mass. What's the mass of H2? Grams per mole, right? Okay, so that's 2 hydrogen atoms put together. What's the molar mass of carbon dioxide? 44.01. So I heard somebody say it, thank you. Grams per mole. All right, so we have this one and we have this one. Which do we want to call number 1? Why are we putting helium? Because it's the lightest one. So this will be number 1. This will be number 2. I mean hydrogen. Sorry, we were saying helium so much earlier. Hydrogen gas. Good. I just repeated what somebody else said. I'll blame them. All right, guys, we're good. It's good. We can read. All right, so moving on. What is the equation to find the rate of diffusion?
2.06.
Well, hold on. I'm not plugging numbers in first. Give me just the generic equation.
Rate 1 over rate 2 equals square root of molar mass 2 over molar mass.
Beautiful. Okay, so let's actually, this is what we have, right? Let's plug in the right stuff now. So rate 1 is going to be talking about who? Hydrogen. Okay, rate 2 is who?
Carbon dioxide.
Carbon dioxide, okay. And then square root of molar mass of who goes on top?
Carbon dioxide.
Good, because it's inverse. Good, so carbon dioxide goes on top, so that's 44. 0.01 grams per mole. Yes, this is a good example. What goes in your folder again?
An example.
Well, I know that. Okay, so equation, description, right? Formula, example, like with the problem solving process, which is a good example, and then if there was a relationship like direct or indirect, you put that as well. Yeah.
Only thing I think is safe to do like inversely proportional.
Mm-hmm. Only for the first three, yeah. Because all these other ones, I mean, you could put inverse here, but not all the other ones have that. Okay. All right, so we're dividing by what here? Grams per mole. What units cancel? Grams per mole. Hunter, what's 44 over 2?
22.
Okay, so what's approximately the square root of 22? Let's approximate, guys, before I move on. What's the square root of 25? I heard 5. So 5 times 5 is 25, right? So square root of 25 is 5. So this is going to be less than 5. So let's say 4 and some change. Okay? Calculate. Calculate the square root of 44.01 over 2.06 or 2.016. Well, we just estimated. I want the actual answer. The calculators are right behind.
So it's really like 20, something like that. 4.6. How much you left?
All right, 3, 2, 1. Answer. 4.672. I'm good with that. Okay. Okay. All right, guys, we got this random number, 4.672. What does that even mean?
That is the relative velocity.
Can you give me more? Give me one sentence, but use the two gases involved, because it's true. That is the relative
It is the
velocity.
relative velocity of hydrogen gas to going to carbon dioxide.
What do you mean going to?
Dividing.
You don't have to use the word relative velocity. Can somebody else give me something else? It's close, Nathan. It's close.
Thank you.
Go for it, Matt. Yes. So put that in a sentence. I'll start off. Hydrogen gas. I'll say hydrogen gas.
4.672 times.
Faster, okay. So is 4.672 times faster than carbon dioxide gas. Good. So you could say the velocity of H2 is 4.72 times faster than the velocity of CO2. You could say hydrogen gas effuses at 4.72 or 672 times faster than CO2. Regardless, I want you to say the lighter one is X times faster than the slower one, or the bigger one. You guys good with that? All right, so I hope that you've added something to your folder with this. I have one more problem for you on Graham's law. Give me a thumbs up when I'm good here. Okay, this one's phrased differently. You're not solving for the rate itself, you're solving for something different. Okay, try that one out. I finished checking on homework for a second.
Actually, no, that's okay.
Yeah. What is the molar mass of the gas? We said, so we would do krypton. We would do the little That's what I always thought. I guess it's a real thing.
Alright, I'll come back and check it in a second.
Okay, so it's 40. Do 84.
Alright, so I want to know how you guys set this up, okay? So you guys had, what was the thing you didn't know this time? One of the identities, right? But what did you know that was interesting? We weren't given individual rates, we were given what?
One rate.
The overall rate.
Oh.
Ashley, with me? So you have rate of something over rate of something. So how do you know who's 1 and 2 here?
Well, it says that the first one's always first.
The number 1 is always the lighter one. So who's lighter here?
The unidentified one.
Okay, so the elemental one is faster, meaning we know it's lighter. Okay, so I'll put question mark here, rate of question mark. Who's the slower one? Krypton, okay, is equal to the square root of molar mass of...
Miss Hello,
Yes?
would you send Alicia for this missile?
Thank you.
Thank
Alicia,
you.
finish watching the rest of these notes, okay? Alright, back with me. Molar mass of who goes on top? Well, who's that in this case? Krypton goes on top, and then molar mass of question mark goes on bottom, okay? But we happen to know, actually, this rate ratio. We know it to be what? 4.5 times. Good. Okay, so essentially we have 4.5 is equal to, what's the molar mass on top? 84.798. Oh, it says 83.3. I'm just using 83.80798. Yeah. I believe. How many people have that on their periodic table? I got 83.80. That's really off on those periodic tables, isn't it?
Wait, isn't that like a really big difference?
Yeah. You just looked it up. Well, no, I'm looking at periodic tables. What's the standard?
It says 84.
84.
Alright, I'll use that. It's cool. It's fine. We have the process. Okay. Over x, because x is my unknown. I don't know what the molar mass is. Okay. So how do I mathematically isolate x?
You have to, no, well, first you have to square it.
Good. Okay, so square root's here, right? So I have to, what's the opposite of square?
Square.
Opposite of square root is
Square.
squaring it.
So then 4.5.
Okay, and then 4.5 also has to be squared. Okay, so then we have this just now removes the square root. So it's 84.79 grams per mole divided by x is equal to, what's 4.5 squared? 20.25. Okay, so then how do I get x out of the bottom? Multiply by x on both sides. Okay, so that cancels over here. And then what? Divide both sides by 20.25. Divided by 20.25. Okay, so it's 84.79 divided by 20.25. 4.18. Okay, so we have that equal to x. What units will this be in? Because it is a molar mass, right? It should be grams per mole. Okay, so the question now is, it says 4.187 grams. The question now is, given that fact we know the molar mass, what would be the identity of the gas? Approximately, right? So this is still approximate, but it should be helium. Good. So you solve for the unknown identity because you need the relative rates of each unit. Okay, so let me pause for a minute because I'm gonna lecture some more at the end, but I'm gonna pull up problem sets 14. I want you guys to look through. I'm gonna do the last half. I'm gonna set it up here. You won't see very many Graham's law right now. I want to say you'll see a few of these. You won't see very many yet, but I do know that some of you guys have questions for each other or for me. So there's 10 through 17. Talk, work through some of those, and you finish taking homework.
Oh, just kidding. I probably didn't get done either. Is that Chem 1? Hold up. I thought we only had to go to 12. Oh my gosh, I didn't know where I thought we only had to go to 12. Well, I didn't want to go to yeah, no, I didn't complete the whole thing either. Look, I stopped it. Oh. See? There's 9, and then well, I didn't finish. Did I?
Let's focus on these rounds. Let's start focusing.
I don't know how much space is
I can on the back of that too. I'm good at no, because I know I did it. I just like, what?
Oh, yeah, that's right. Yeah.
Oh my God, I'm sorry. I'm staying in front of the board. I literally got that. Look, I started off right now. Are you gonna do any more right now? Huh?
Oh, no. This is not wow. Sorry.
Alright guys, I've already warned 5 people to stay back on task. I'm trying to give you homework done. This is the behavior that stops allowing me to let you guys do your homework in class. Okay? So please focus. I didn't say you couldn't talk. I just said focus. When you guys can't focus and talk, that's when
You still won't probably. What ones are you again? Combined. Right? 20 grams.
One key is 156.5. Whatever it's called.
No, you don't. Look, even though it's cool, it's equal to 1, 3. Is the answer right?
But then it says
Yeah, but I wasn't even given the How did I get that?
no, it's because you have to get the standard pressure. That's the standard pressure. And the problem is, what is the volume of chlorine?
Yeah, it's called I don't think it's combined yet.
STP has APAL degrees. So it's combined, right?
Number 10, this is liters.
There's no what of yeah, only and then you can take your volume and pressure.
That one.
Where's the other temperature?
In the S.
Mine? I don't know. It says more.
Since it's STP, STP is still temperature and pressure is the temperature would be and the pressure is 101.
Oh! It's 2.09. Up there, it just says. Wait, so you said 3. Oh! You said alright, that's right. I got one. Like,
And the volume is yeah, okay, so we have the pressure is 101.3
Number 11 is also
13.
number 10.
No, I'm trying to get this. Well, so can you just an example of it? Remember, like, you need to, like, find out what it is.
Okay, right.
Just talking about small numbers. Watch sick things, but other than that, you're good. No, I'm just gonna write.
Wait, so you can't use
Okay. I'm looking at what laws. Yeah.
Alright guys, take one more minute where you are. Take one more minute. We'll have some more time at the end.
Which one are we going to So you calculate this side, and then you calculate this side to be about S.
Oh yeah, I remember. Okay.
I totally like found out.
That's my opinion.
Oh, that is
Alright, yeah, I have to show you. Well, you can't do 15, 16, 17 until I teach you what we're doing today. So after that, we'll pick it back up there. Okay. All right, guys. Yes. Quick question, Aishi. Which one?
ideal.
15.
Yeah, I think so.
15. So what we're gonna piece together now is that ideal gas will be in just a normal question for ideal gas, or the ideal gas will be involved with reactions. So when you start hearing reactions, like look at 16. Sodium carbonate decomposes, right? So let's go ahead, maybe make a space on some paper, write 16 out for me. It says sodium carbonate decomposes. Well, I need the formula for sodium carbonate. Anybody got it here?
Nope.
So, sodium has a 1+ charge because look at what group it's in, guys. It's in group what? Group 1. What's carbonate's formula? CO3 charge. -2. So crisscross. What do you get here? Okay, everybody's writing this equation down with me, okay? Sodium carbonate decomposes. So as you're thinking about carbonates and decomposing, you're thinking about those foldable, right? The reaction type foldable we did. And there were 4 types of decomps, right? Think hard. What does a carbonate always make? Metal oxide and carbon dioxide. Well, we better make it a gas, right? Ideal gas law. Ashton and Nina, guys, with me for a minute, okay? So we know we're making a gas. We're making CO2 gas, right? Carbonates make carbon dioxide. And somebody said metal oxide. What's the metal here? So sodium oxide. So what's the formula for sodium oxide? Na2. Good. Oh, because that's sodium with a 1+ charge, oxygen with a -2 charge, and we crisscross those charges. Okay, so is this balanced?
Yeah, no.
I think it is actually.
It is.
Yeah. So here's the BCE for number 16. Perfect. Because as you look up further at 16, it says, liters of gas, pressure, and temperature. How much of the sodium carbonate decomposed? Notice it didn't even ask about the gas, right? So here's the problem. We have the ideal gas law, which we have to plug what into? Stuff about the gas, right? Carbon dioxide gas, but then it wants us to relate carbon dioxide gas all the way back to sodium carbonate. Well, how do I relate product to reactant? How do I go from here to here? I have to have more ratios, right? So the stoichiometry piece comes into here a little bit, but not like so much it's overwhelming, okay? So let me tell you about the stoichiometry piece now, and then we'll go back and finish up number 16. Yeah, I only have about 3 slides of notes, so just, write down what you need to, but specifically do the example problems we can put together.
So what are we?
We're going to do reaction stoichiometry notes. So call it like gas stoichiometry. Gas stoichiometry. Write down something first and then we'll talk.
Wait, what did we write down for
Kinetic motion theory.
Wait, why would you? C or STO. STOI. Oh yeah. Yeah. I was almost there. I don't even like here.
This is why he's a genius.
Alright, so some of you guys were finishing a conversation. I appreciate you halting that now. Thank you. So I'm going to focus on the middle of the board first. Who remembers this number?
I do.
22.4. You've seen it before, and you guys all wanted to use it with molarity, but I said no. You have to only use it with what?
Volume.
Gases, right? Volume of a gas. And then back in the day, I was always saying like, oh yeah, gas at STP, and you were like, yeah, gas at STP, but you didn't really know what STP meant. But now we know what STP means. What does STP mean? So what's standard temperature?
0 degrees Celsius.
Or 273 Kelvin. Okay. Now what's pressure? Oh, okay, all those, right? Okay, 101.3 kPa, 1 atmosphere, 760 millimeters of mercury. Okay. So we know there's a lot of those, but in general, those have to apply. Those have to be the conditions if we're going to be using this conversion factor. Remember, we wrote it as like 1 mole per 22.4 liters or vice versa. Okay, so, but what we've been now exposed to is, do we always have STP? No, so there must be a backup plan if we ever have to convert from moles to, from conditions given to moles. So this is it if we have conditions given in STP, but if we don't have STP conditions, we have to use the ideal gas law. Okay, so we must use the ideal gas law. I'll go back up to the top first. So a lot of times we'll be given maybe moles of one substance will convert to moles of another substance, or at some point in time we're going to use a mole ratio, or at some point in time we're going to use the ideal gas law. So I'm just going to put ideal gas law and reaction stoich, because we're probably going to have to do these together in order to solve a problem. And that's what's on the next slide. But before I do that, I'm going to backtrack to the top. This is just an example, like saying if you found something about the moles of the gas, you could get to N of this gas, and then from there, take your moles of the gas and go to grams of the gas. Well, how would I go from moles to grams? Your table of molar mass, right? So that we know the ways to get there. It's just we need to do a problem to make sure we're remembering it, because that was a little while ago. All right, so back at the very top, let's pretend, and question 16, it asks for like grams of the sodium carbonate, but let's refresh, let me revise this question for a second. Let's say it was asking if given a certain amount of grams, let's say we're given like 10 grams of sodium carbonate, and the question was get to volume of CO2, we have to find a way to do that, right? So I know I can't do crap with grams. I'm probably going to have to do grams first. Convert to moles. So from grams to moles, you're saying use what? PTOE molar mass, okay? And then I know that I'm going to have to eventually plug this into the ideal gas law. So can I plug in a solid sodium carbonate into the gas law? No, so I have to get from moles of this to moles of carbon dioxide. How do I get from A to B? Mole ratios, right? You guys remember crossing that bridge with mole ratios? Where do we get the mole ratio from? Right, BCE, balanced chemical equation. You guys remembering this a little bit? Yeah. Coefficients matter. Okay. So now once I get from that thing to this thing, I'm in moles, right? I've got N. So now that I have N, and let's say I have B is my question. Let's say I had P and T. I have P, N, T, and V. What gas law is that? Ideal gas law, right? And I can solve for the piece of unknown, which would be V in this case. That's the scenario I gave you. That's it.
That's not
Well, it's just combining something we did to something that's our ideal gas law. It's not bad once we see an example. Give me a thumbs up when you're ready to do the example. This is all like theoretical, like this is what you would do if you were given this, but let's actually do one.
It gotta be one.
It's not bad. Okay, and then so a couple of you guys asked me, and then I'm thinking that because we're talking about reaction prediction again. When we finally have intervention again, so next week we'll do that revised reaction stoichiometry quiz. Printed, ready to go.
Oh.
It won't take you but 5 minutes, so keep looking over that reaction stoichiometry, reaction prediction, like predicting the products. 4 of you I think got 100, you're good. But the rest of us are gonna get hundreds. Okay.
Oh, the one that you said to retake?
Yeah, the one you're gonna retake until the day you die. Okay. So go ahead and write down the givens from this question. Okay. Write down the givens from this question.
Alright, yeah, I got it. Wow, you say that because I didn't know. I think this was like super long. Like written out. Would I have enough for me?
I don't know how big you brain memory. Just leave some space.
That is true. Just that I don't know how big you are.
Alexia, give me one given you wrote down.
The pressure is 755.
Millimeters of mercury. Okay. Ashton, give me another given.
The temperature is 130 degrees, but it's 296 Kelvin.
296 Kelvin. Alexia, figure out what that is in atmospheres for a second. Alex, give me another given.
The volume is 42.6 millimeters.
Okay. And then there's one more kind of given slash question. Courtney, what's here? What's the question? Okay, so potassium chloride is a given, right? But it doesn't. Oh, I didn't say that. Guys, what's potassium chloride? Gosh, I'm so just like out of it. Okay, so potassium chloride. How does that decompose, Josh? It is cumulative. Say again. There's no carbon. Josh, there's no carbon. Metal chloride and. Good job. Okay, so we knew that we weren't going to make chlorine because chlorine gas would kill us all. Okay, good thing you guys remember that. Okay, so oxygen gas is our gas of interest. And then thank you, you said potassium chloride. Yeah, and these all have one charges, 1 plus 1 minus. That's why we don't see extra subscripts. Balance that, everybody. Okay, so check, we have a BCE, and check, we basically, I don't know if you guys can see this, but do you see that this is starting us on the ideal gas law? Because we're not given 2 pressures and 2 temperatures and 2 volumes, so we're not given 2 of everything. It can't be any of like the Boyles and the Charles and the Gay-Lussac's and combined. It can't, it just can't be. So what thing are we missing here for the ideal gas law? And so we're technically going to solve for moles of what? Moles of what? No. This is the ideal gas law, so we're solving for moles of oxygen. Okay? So that's really what we're looking for. So I put the O2 so you remember what we're solving for. But what's the end final question we need? So that's up here. What's much mean, guys? Much means grams. Okay, so the real question is grams of potassium chloride. So let's walk through this before we start solving. Okay, so off the bat, you know we're going to have to do what to solve for N? Ideal gas law. Perfect. Okay, so we're solving for ideal gas law, solving for N. All right, so once I get here, I interpreted the yawn. It worked. Okay, so once I get here, How do I get back to potassium chlorate? I hear 3 and 2, right? So there's our mole ratio. Once I get to mole ratio back to moles of potassium chlorate, how do I get to grams? Paratable mole mass, right? Things that we know. So let's do the ideal gas law first. I noticed that I have all my units except for P and V, right? So what does P have to be in? I think Alexia was getting that for me. Well, what is that in atmospheres?
Oh,
And then everybody tell me what this is in liters. 0.04. Okay. Alexia? 755 divided by 760. 99 what? Just 99? 34. I mean, you know, I need some sigmas, right? Okay. So 0.9934. All right, so I have ideal, so PV equals an RT. All right, dividing by what to solve for N? Guys, divided by what? Divided by RT to solve for N. Okay, so R and T cancel. So N is equal to PV over RT. So N meaning moles of oxygen is equal to, what's P, Hunter? Did you not write this down on your paper? 0.9934 atmospheres. All right, Hunter, what's V? What's V?
2.6.
0.426 liters. Good. See how I'm writing my units, guys? We should all take a hint here. Make sure you have units on everything. Next, guys, R. 0.0821 atmospheres times liters over moles times K. Woo! All right, hot dog is a big one. All right, and then temperature. 296 Kelvin. All right, everybody cancel your units. Show me what's canceling.
ATM.
I heard Kelvin first, okay. I heard ATMs, and I hear liters. What's the only thing left? Moles. Remember, copy dot flap or multiplying by the inverse. The moles in the bottom eventually get back up to the top. So that is solving for moles. Yay. So what's our moles of oxygen when you guys get there? I hear 0. So make sure you guys calculate. There's more to that. 4. 1.6. I'm good with that. That works. Okay. So let's double check we calculate correctly because I don't want you guys to know the step and then not be able to reproduce on the calculator. All right, kids, we made it to moles of oxygen. We're still not to grams of potassium chlorate. How do I get from here? All right, so I'm going to take my moles of oxygen. What goes on the bottom? Where am I getting this 3 from, Ethan? Good, so 3 from the 3 moles of oxygen. And then everybody else, what goes on top? 2 for the potassium chlorate, so 2 moles of potassium chlorate. And then, so moles of oxygen will cancel. And the question is still getting us to grams of potassium chlorate, so what's my last and final step? What goes on bottom? Right, 1 mole, not just any mole, so 1 mole of potassium chlorate. And what goes on top?
122.551
Grams of. Good, so that's the molar mass you calculate from the periodic table. Good job. And then moles of potassium chlorate will cancel, and that gets us like 0.42 and some change. Let me calculate that line. One four. I knew it was 4. 1 4 what? 142. So just a little tiny bit of potassium chloride, just a smidgen of potassium chloride, decomposed. It made how much gas? Right, so about 43 milliliters, so you have like that much. And that's actually what we did in the gummy bear experiment. We made it molten, it decomposed after a gummy bear, and it went. Remember that? Okay, and that's because we made oxygen gas, which is flammable, and when I put the gummy bear in there, it was like the fuel for the fire. Okay. I don't have gummy bears on me here. Okay. So we're gonna go ahead and finish 16 now. Okay. I got you started. Go ahead and finish 16 and 17. Let me make this a little bit bigger here. We still have like half an hour, and the last thing I want to do is actually start your other homework with you, 1 through 5. But I know that we're not going to finish it today, so I'm going to let you guys work on this for a little bit longer.
I'm not a joke anymore. I don't know.
What number is 16?
16? Do you ever do 13?
All right, get ahead where you can for the next couple minutes.
Try 100.
All right, back to me in 10, 9, 8, 7, 6, hold this paper, 5, back to this, 3, hold this paper, 2, 1. Okay, so I have one last set of questions that we're going to do, but I won't be able to do them all in class. My thought was that we'd be doing 1 through 5. You guys see this on the bottom beneath, like number 24. Okay. My thought was that you guys would, the challenge would be presented to you is to combine stoichiometry and ideal gas law. I will do 2 of these with you right now. I want you to do at least one more tonight. So some of 1 through 5. That's what this is regarding. And then what I'll do is I'll see how much more we need, and then from there I'll decide if I'm going to take. I am going to take these up. Okay, so if it's on paper that you don't mind me taking, it's okay if it's in your notes. I got you graded pretty fast. But if we don't have to do all of them 1 through 5, we don't have to. But I won't really know until I see how well you're doing. Okay, so work with me here. All right, so call this gas stoichiometry. Gas stoichiometry. I will model one more time how to do these, but I want to make sure that you're helping me out as we go. Okay. So when 4.5 grams of magnesium chlorate decompose at 800 degrees Celsius, 5.94 liters of the gas is collected at 774.0 millimeters of mercury. What is the percent yield, right? So we're bringing back, it's very cumulative, we're bringing back some old stuff. So Garrett, before I move on, what is percent yield? What's like the idea of that? I guys, I'm asked for one person, I really do mean it. Thank you, Garrett. You said actual yield over theoretical yield. Times 100 gives us percent yield. Good. Okay. So as you have seen now so far, all of these gas stoichiometries include like ideal gas law and what? A little bit of what? BCE stoich, right? We need a balanced chemical equation before we can even start attempting the stoich. So let's get this balanced chemical equation first. Write down magnesium chlorate. I want you guys to decompose that. See if you can predict those products. This is good practice for those of you who still have to take that quiz. Magnesium chlorate decomposes. Alright, Ashton, tell me one of the products. Shh. Ashton. One of the products. You could have CL. Two. Okay. Guys, everybody remember magnesium. You don't have to remember it. Everybody look at magnesium. What's the, what group is it in? Group 2, so it's a 2+ charge. Chloride's in group what? 7, so it's got a what charge? 1-. Okay, so MgCl2, and then Josh, give me the other product. Other product. O2. Good, so we have to make a gas. If not, we're not going to ever be able to plug into the ideal gas law. Parker, balance that.
2. No. You need to put 3 in front of the O2.
Very good. Good job, Parker. Yeah. Everything else is balanced. Okay. All right, so give me one of the givens, Langston.
4.5.
Magnesium chlorate. Okay. Give me another given, Olivia.
5.94
Okay, what variable is that?
volume.
Okay, so V is equal to 5.94 liters. Will, give me another one.
800 degrees Celsius.
And what is that?
So it would be 1,000.
So temperature is 1,000.
92.
1,073, right?
70.
Yeah, okay. So we didn't even write the Celsius down, we just went straight to Kelvin, good. And then one more, everybody. So pressure, P, like now I guarantee you this helps if you guys write the variables down. Some of you guys are just writing the numbers down, I think, but it helps you to see the gas law if you write the variables down as well. So P is equal to 774.0 millimeters mercury. Get that out of here. What do we want instead? So how many atmospheres is that? So you're multiplying by 1 atmosphere over 760 millimeters of mercury. So technically just dividing by 760, what is that? 0.02, thank you, atmospheres. Okay, so we've got VTP, and then what's it ask for? Percent yield, right? So it doesn't really guide you where to go, but let me help guide you. So, percent yield, actual yield and theoretical yield. So we're kind of in two pieces here. VT and P is all going to be combined into the what law? Ideal gas law. Okay, so what are we missing? Yeah, N of what? No, don't you be plugging anything but a gas in the gas law. Right, so moles of oxygen. Good. That's our actual question first. Moles of oxygen. Remember, all this junk here is going to be regarding a gas. All right, so do you guys think, when I find moles of oxygen, do you think that these moles of oxygen are going to be actual yield or theoretical yield of oxygen? Why do you? I hear most of you say actual. That's true. Why? Well, yeah, it says the gas was collected at this volume and this volume and this temperature and this pressure. This is talking about an experiment, right?
Theoretical would be STP.
No, we're going to talk about what that is in a second.
Convert 4.50
Yes.
of that using the
You would convert this using stoichiometry to what?
to
Well, it's got to be the same units, right?
moles of
Moles, right. So put ideal gas law, something like that. I've kind of bracketed mine off, but this is going to give me actual yield. This is what the student did in the lab. But what they should have thought, what they should have done was, okay, like if I have this many grams of magnesium chlorate, I should theoretically, on paper in La La Land, be able to make X amount of oxygen. So this we're going to get theoretical yield from by doing stoic. Okay? All right, so what do you guys want to do first, stoic or ideal gas law? Okay, ideal gas law it is. Okay, so let's go ahead and do that. PV equals nRT. So you're always going to have both of them, FYI. You're always going to have stoic and you're always going to have ideal gas law. It's kind of up to you which one goes into play first, because sometimes the data tells you what to do. This one we could do either first. All right, so we're solving for what? right? So divided by RT, good, divided by RT. So N is equal to, what's P? 1.02 atmospheres, okay? What's V? 5.94 liters, good, divided by, everybody's working this through with me. Please be very organized with this, because if I don't see units and stuff, I just can't give you credit on that question. Each question's worth 20 points. There's only 5. Okay, work with me. I'm doing the first one with you, okay? So, 0.0821 atmospheres times liters divided by moles times K, good, Kelvin. All right, and then the T is what? 1073 Kelvin. Okay, everybody, what you cancel here? Okay, so Kelvin here and here, liters top and bottom, atmospheres top and bottom. Only thing left is moles. Calculate moles for me, people. And Mac, these are moles of what?
Oxygen.
Thank you. Alexia says 0.0 what? 0.0687. Good. Moles of oxygen. Okay. Everybody label this what yield? Actual. This is actual yield. Good. All right. La La Land theoretical yield now. What do I start with to find La La Land theoretical yield? The grams of what? Magnesium chlorate, right? So I've already used this volume, this temperature, this pressure. I found moles. I can't use that again. That's all for the actual. So let's go ahead and take 4.5 grams of magnesium chlorate, and you guys do the story. But remember, if we're doing yield, right, we're still talking about a product, and actual yield was in moles of oxygen, so what does your theoretical yield have to end up being? Moles of oxygen, because I can't compare liters of oxygen and moles of oxygen. I've got to compare the same thing. Do stoic here. You guys have the reaction right on the top of your paper someplace. 191.2, 191.2.
Like in a minute, okay? So I'm about to keep up in a minute. Okay. No, I'm serious.
Yeah, or no, 3 to 1. 191. Parker, you have this on your paper, right? This week. It's like true. Alright, so what was the first step, guys? Converted to moles, right? So what goes on top? 1 mole magnesium chlorate, and what was the mass of that? 191.2 grams of magnesium chlorate. So we just converted to moles from, we just converted from grams to moles. Ooh, okay, grams cancel. Great. Okay, so I'm still not to the gas. That's my last step. Okay, where am I pulling mole ratios from? Okay, so which two do I care about? Magnesium chlorate and oxygen. So that's a what to what ratio? 3 to 1. Good. So I'll put 3 moles of oxygen on top, and then 1 mole of sodium, whatever that is, magnesium chloride on the bottom. Whew. All right, and then how many moles is that, guys?
0.0706.
All right, and this is what yield? Oh, sorry, this is theoretical yield, right? Okay, so then to actually find the percent yield, now we can do whatever way. Actual yield over theoretical yield times 100. So If you're waiting on me, go ahead and get started on number 3. I'm skipping 2 for the moment. Mainly because I think it's limiting your agent from memory. I know you don't want to do that right now. I feel you. %, yield, yay! Would you let that person be your lab mate?
Yes.
For sure. Let them do the lab. Maybe 1 out of 10 who kind of understood what we just said. 10 means you're the bomb.com. 1 means you are totally opposite of bomb.com. And mostly 2 hands. Okay, good. Hands up. You're good. Use your hands. Okay, I just wanted to see where we were. So, reminder, you see a question like this, and it says reactions occur. Write the reaction down first. Right? Write your givens down first. Then think forward before you start solving. So we thought forward. We were like, okay, what's % yield? It kind of helped us to determine what was going on. And then we did ideal gas law first, and then we did stoic. And from there, we compared our actual and theoretical and got % yield. Easy. It's just tiring, yeah. All right, so let's just get started on 3, only because I know that you can get started on your. Oh no. Okay, there's 3. It's not a race. Okay. All right, go back to, sorry, you guys got this right here. It's on your paper. Write down your givens and your reaction. Givens and reaction. This one's very doable. This one's easier than the last one. All right, Serena, I know it's kind of early, but I think you can tell me this. What is one of the products of this question's scenario? What's the product?
That would be ammonia.
Good, so it's saying blah, blah, blah produces, right? So it's saying produces ammonia, NH3. And then it references something else. What does it reference?
Yeah.
Which reactant, though?
Nitrogen.
Nitrogen. So guys, how are we writing nitrogen out here? N2. So then you got to figure out what's the other reactant? It's got to be hydrogen gas, right? So it's talking about the elements. So what's this balanced chemical equation?
4, 0, 1, 4,
No.
No, oh, it's
1, 3, 2. Good. Okay. So now we have the reaction. We're good to go. We know this is our BCE. All right, everybody, tell me the givens here. So what variable is that? Volume is 48.6 liters of what?
Ammonia.
Ammonia. So I'm going to put B2 or BNH3 like that to remind me that this is ammonia, because I'll forget in the end what I'm talking about, okay? Keep going. What's another given? So that's T for temp is, give me that in Kelvin. 283 Kelvin, and then what else? P is, so 70.91 kPa. I got to convert that to what? So 1 atmosphere is equal to 101.3 kPa. What is that? 0.7000, and it was actually exactly that. Okay. Okay, so what am I missing? The what? Amount, right? I'm missing moles. So, Mac, moles of what? See, the thing is, they're all gases here, so you really have to pay attention. Which gas? Nope. The volume was given for whom?
Ammonia.
Ammonia. So the moles must be regarding the same thing, right? So that's why I wrote ammonia early, so you would remember that this is still ammonia. Ammonia have you ever smelled caffeine? That's ammonia gas hitting in space. Okay. All right, so we have everything we need except for moles. So I'm going to plug this into the what? Okay, I'm going to plug all this into ideal gas law. And I'm going to solve for moles of ammonia. Okay, so what's the final question? Okay, so grams of N2. Okay, so once I get to moles of ammonia, what am I going to do? Mole ratio back to moles of nitrogen, and then what? Okay, molar mass. Okay, knock it out. Knock it out.
I'm gonna get her love.
I'm going to do stuff back as soon as I can. Yours are great today. Keep processing this question if you are. I do have a couple things. I've put a lot of zeros in recently because people are just not turning labs in. And once I grade lab, I'm probably not taking labs like after that. So
Good afternoon. Bus changes for the day. Bus 308 will be 15 minutes late. Students are to wait in the commons or call home. Thank you and have a good afternoon.
Thank you for helping.
I'm not kidding. I have. Might not be that. Oh man.
S'more yum. Well. Nathan Moore. Alex. Olivia Williams.
Is the only lab she's talking about the small one? Is she only talking about the small one?
I don't know. Take this. Or I just keep it. Take it. It's 100. I don't care about it.
Dear tutors, please report to the front of the media center after school today for your yearbook photo. Again, dear tutors, please report to the front of the media center after school for your yearbook photo. Thank you.
Yes, 14.92. I've got a couple questions up there. I said do some. Do some.
I usually.
If you get started on it, you can finish tomorrow. Okay.
Yeah, he's gonna hold it all day and remember to give it to you tomorrow.
I'm gonna forget. Can you just give us? We'll give it to you tomorrow. Thank you.
Are you going to see it back to your house?
Hey guys. What's up?
For our scientific scientist project, like my uncle, like he used to like work in the industry with like making like the dry fructose.